Okay, so, we are looking at description logics, and there are essentially 3 kinds of sentences in DL. And we are basically interested in asking whether those sentences, such sentences are true or not, which means we are interested in the questions that does the knowledge base entail whether a concept is subsumed by another concept. So, this is D subsumed by E, or does E subsume D. Then we are interested in asking the question whether 2 concepts are equivalent, which is equivalent to asking whether they subsume each other essentially. So, that can be answered if we can answer the first question. The third kind of question that we want to focus on today is whether an individual A belongs to a concept D essentially. Does A belong to class D? And this is the task of satisfaction. This is the task of subsumption, and these are basically the questions which ontologies, when people create ontologies, and a lot of people are creating ontologies because they are useful, because for example, in e-commerce you are building systems, repositories of what kind of things you are selling. So, books and authors, and who are the authors, and music, and everything that is in the store, for example, is described using some ontology. And then you may have programs which talk to different ontologies. So, for example, that there are programs which say that find me the cheapest copy of let us say a movie or a book or something like that. How do they do that essentially? Because different stores, the way they represent that knowledge base is really internal to them essentially, that they do not necessarily have to conform to some common standard essentially. The interest in ontology is to try and move them towards some sort of a common standard essentially. So, if you have looked at ontologies, we sort of very briefly discussed RDF at some point essentially. So, you have some XML namespace, and then you have RDF namespace, and then there is this OWL namespace where all these things like subsumes and subclass of and that kind of stuff is defined essentially. So, the question that you want to ask is whether a given individual is an element of a certain class or not essentially. What is a knowledge base? It contains statements like some concept D1 is defined as and some D2 fills and whatever, some statements essentially. So, D2 is defined as, so we are assuming here that we use the equivalence here to define some things and so on. Then you might say individual A belong to D1, then somewhere else we may say A belongs to D2, and so on and so forth. So, a knowledge base is the whole idea of a knowledge base is that you can keep adding new facts or things to that, and essentially the system should be able to handle it essentially. So, sometime you might say for example, Neha is a table tennis player, somewhere else you might say that Neha is a professor, and somewhere you might have said that she is a female and she lives in Chennai and so on and so forth. And then you know a lot about an individual and you want to ask a question. For example, does Neha belong to this class D 1 that we defined a couple of classes ago, which was a set of all people who are married and who have at least 2 children and all whose children are sports person and who at least bank with one bank. Is Neha belong to that class or not? To answer such question is a task of satisfaction, and we want to focus a little bit on that today essentially. So, the first thing we do is collect all information about each individual together essentially. So, for example, so if we have this and if we have this, then we can replace it by a statement which says A belongs to and D 1 D 2 which is equivalent to saying A belongs to D prime, which is normalized version of this statement essentially. So, the first thing you do is you collect together everything about that is known about an individual and construct a class for that, and then attach A so in the taxonomy so I should say attach So, there are two possibilities that either this D prime is present in the taxonomy or D prime is not present in the taxonomy. So, when we say the most specific class it belongs to, we basically mean D prime is subsumed by some D I and this is the most specific. So, at the lowest possible place in the taxonomy you attach A essentially. So, every individual or every constant you attach it in the taxonomy to some class, which class? The most specific class which describes A essentially. Once you have done that, so what is the situation? That means you have this is the top and there is some taxonomy here and there is an individual called A and we attach it to some class which we call let us say D, and now if we have a query E, we translate this query into another query which is equivalent, which is asking the question is. So, this is a query D subsumed by E. What is the rationale behind this? That if you have some class E and we are asking that does A belong to this class E, for example, does Jane live in Chennai, or does she belong to the set of people who live in Chennai, then we have a complete description of Jane, for example, which says that she is a sports person and she is a professor and whatever we know about her, and that is the concept D to which she is attached. All we need to answer is whether if D is subsumed by E, because if she belongs to D, then she definitely belongs to something which subsumes D essentially. So, you can see that this question of satisfaction we have translated into a question of subsumption essentially, which is why our focus was so much on finding an efficient algorithm for subsumption and also constructing the taxonomy explicitly essentially. Even if our algorithm for subsumption, as we will see in the next few classes, that you can have languages where the structure matching algorithm does not work essentially, and then you have to resort to other more expensive algorithms. But even if you have done that, once you have constructed the taxonomy, which means all you have to do is to now find a path from D to E, and then you have answered the question that A belong to the class E or not essentially. So, that is a rationale for constructing the taxonomy and having it explicitly represented essentially. Then you have to just do traversal and so on and so forth. We can also answer questions like who are the individuals that satisfy a concept. So, I use the term concept class interchangeably. Let us say D, some concept D, or let us say some D3 or something like that. So, if there is some concept D3 sitting there in your taxonomy, you want to know who are all the individuals who satisfy this concept D, then all you have to do is to explore the tree below that, look at all the nodes which are sub concepts of D3 and find all individuals which are attached to them essentially. So, let us say there is A1 here and let us say A2 here, let us say some B here and so on and so forth. You just need to traverse the tree below D3, collect all the individuals which are attached to concept there, and the answer is there essentially. Explore sub, let me use the term taxonomy here, below D3 and collect all the elements from there essentially. You know that your answer will be correct, because you have taken the trouble to attach every individual to the most specific concept that you could find essentially. So, there is no possibility of it being attached somewhere when it was actually belonging to the class D3, because it would, if it belongs to the class D3, it would either be attached to D3 or to a descendant of D3 essentially, because you are looking at the most specific thing essentially. But nevertheless, there is a problem essentially. Okay. If you are looking at this problem of satisfaction, there may be implicit information and the example given in the book, that one of the books that we are following, Brackman and Levesque, is as follows: that supposing you know that Joe is a person, and that is all you have said about Joe, and you also know that there is a company called Can Corp, which has the following description, that it is a company and all whose managers are Canadian, and somewhere along this there is also a sentence, Phil's manager Joe, and there are other stuff. Remember that we are putting together all. So, in our strategy for this company called Can Corp, we would have collected all information about that, as to know who are the managers and what else, whatever information we have for the company we will collect it, which will include, for example, Phil's manager Joe amongst other statements essentially. So, we had said that the knowledge base will consist of statements like this, but you can see that now that we are talking about this person Joe, we know that Joe works for this company Can Corp, because he is a manager in this company. But we also know that all managers are Canadian essentially. So, this means Joe must be a Canadian. So, when we say that we want to collect all information about an individual, we basically mean whatever is given in the knowledge base and whatever can be inferred from the knowledge base essentially. So, whatever is given in the knowledge base is explicit, but what can be inferred are facts like this, that Joe is a Canadian. But of course, there is also the fact that Joe works for Can Corp, but maybe we have not, our knowledge base does not represent information in that manner. So, we do not keep that kind of information essentially, but our knowledge base implicitly has the information that Joe is a Canadian. So, that we should be able to collect essentially. So, we need to extract such information. Through a process of forward chaining, it is a process of propagation. So, I will describe that here. And the task of here is to make whatever is implicit explicit essentially. So, from the example that we just saw, we can see the following, that collect all pairs of the kind B 1, D 1, B 2, D 2 and so on, where this is an individual and this is a normalized most specific class that it belongs to. Then if there are two pairs, let us say B I D I and let us say B j D j such that so let me just write that example again here. We said that Joe is a person and Can Corp is a company and all managers, I will just write M here, Canadian Fields manager Joe. So, if that is the case, then this corresponds to B j here, and this whole thing corresponds to D j. This corresponds to I am mixing up colors anyway. This corresponds to B I and this corresponds to D I. So, if you find two such pairs where one of them contains information about the other and this D j is not subsumed by E, which means we already do not know that information. Then replace it should be D I, right? No, D j, sorry. So, essentially that is what we said essentially. What does this mean? This step here means we replace Joe by and person Canadian, and this Canadian basically corresponds to this R in this algorithm here. So, we are propagating the information which is kind of hidden inside about Joe, making it explicit and saying that we know that Joe is Canadian, because Can Corp involves all Canadians as manager and Joe is a manager, and we make it explicit. So, we just do this process for all such pairs BI, DI and BJ, DJ essentially. Why are we doing this? Because we want to attach every individual to the most specific concept that it can be described with, and this is our goal, BI with DI, BJ with DJ and so on, where BI is the individual and DI it is a description essentially. There is a case that which is a kind of a special case. Handling statements like this. So, when you are describing some class by saying that it is related by at least n people to some this thing. So, for example, exists in friend, or let us say exist to friend, then there is an individual which is a friend, at least one individual, in this case 2 individuals who are a friend of the person that we are describing or the class that we are describing, but these people are not named individuals essentially. So, for example, if I had said Joe and person, and this clause here exists to friend, or let us, to make life simple, let us just say one friend, and we can extend that argument to more than one friend essentially. So, if you look at this, then we are talking about a person called Joe, but we are also talking about a person called, well, not called something, or unnamed person who is a friend of Joe essentially. And there might be some information which is buried there essentially. So, let me first give an example here. So, if you say that, and this is from the book, Ellen is a person and so we are saying that Ellen has a child, but we are not naming the child essentially. But then we might have some property which is buried in the description, which says that all her children have a pediatrician called Marianne, and all the pediatricians of her children let me use the word Canadian again here. So, you can see it is a very simple, very similar example to the one where Joe works for this company called CanCorp, and CanCorp has only Canadian managers. Here we are saying that Ellen is a person who has at least one child, and the children have pediatricians, and the pediatricians are all Canadian, and Marianne is one of the pediatricians there. So, I might have somewhere let us say some information, since Marianne is mentioned, I might have some information about her essentially. Let's say some DM or something like that, whatever the description is essentially. How do I extract the fact that Marianne is a Canadian? Because we said that look for pairs Bi Di and Bj Dj, but here what are the people we are talking about? We are only talking about Ellen and Marianne essentially. And if we look at Ellen, then the criteria that all and fills is not part of Ellen's description, they are part of Ellen's child description essentially. So, it is kind of buried in the fact that these are unnamed individuals. What is the spelling of unnamed? How do we extract that information out essentially? So, essentially what we need to do is to form role chains. So, here for example, we know that there is somebody called Joe dot friend. So, Joe dot friend stands for an individual who is a friend of Joe, but we have not given it a name. So, we will just call it Joe dot friend. Here we will say Ellen dot child, and Ellen dot child actually corresponds to this description. This will come here. So, this description of Marianne is buried in an unnamed individual who is Ellen's child, and which can be identified by using a role chain. So, basically a role chain simply says that you can talk of an individual A for by let us say aunt sorry let me use example here. So, I might say Ramesh dot aunt dot cousin dot niece dot So, this is a role chain. So, all these are roles, and we are describing some individual using a role chain essentially. Of course, it is very common in our country. So, if you are talking about a close relative, for example, you might say Ramesh's aunt's cousin's niece's daughter is a close relative of but that illustrates this notion of a role chain essentially, right. You identify an unnamed individual by a sequence of roles like this essentially. So, here we have Joe's friend, here we have Ellen's child, and here is a slightly longer role chain essentially. So, we need to adapt our algorithm to handling role chains, and I will leave that as a small reading exercise for you. It is given both in my book as well as in this book by Brackman and Levesque, which basically extend this idea to role chains essentially. And why do we need this extension? Because role chains involve unnamed individuals. In fact, if you look at this role chain at the bottom of this class, there are so many individuals we are talking about. We are talking about Ramesh's aunt, then her aunt's cousin, then cousin's niece, and then niece's daughter essentially. So, at least 4 different individuals we are talking about, but they are all unnamed essentially. So, ideally our knowledge base should also have pairs this B 1, D 1, B 2, D 2 for unnamed individuals which are specified by role chains essentially, and that would make it complete essentially. So, this gives us some insight into how we use description logics to describe domains and so on. The logic that we have looked at, which is described in both the books that we are using, is one of the earliest logics essentially, and I will encourage you to think about what you cannot say using this logic essentially, and then we will try to look at some examples of that, look at why we cannot add such descriptions. So, for example, one thing that we have is that our exist statement says that you have at least n role fillers essentially. Why not at most? Why are we not allowed to talk about at most also? And there are other things that you can say. So, for example, exist n friends essentially, but can I say exist n friends who are rich also? So, they should belong to a certain class essentially. I am allowed to say that people who have at least 2 friends, but can I say people who have at least 2 friends who are rich essentially? That is not possible, and we look at that in the next class essentially.